Hello everyone, my name is Kamalika and today I'm going to talk about building an ISO compliant data center and data recovery center with bare metals using Terraform and VMware. So without any further delay, let's get started. First, let's understand what is ISO compliance. When I say ISO compliance, I mean ISO 27000 compliance. It is an international standard to manage information security. The full form of ISO is International Standardization Organization. This is an organization that releases standards for various practices that organizations should follow, be it information security, infrastructure security, etc. So here in today's session, we are going to be discussing about the ISO 27001, which specifically talks about information security for your organization. So what is the background of the project? So the background here is that one of the leading financial services institutions of Southeast Asia wanted to go live with their applications, and for that they needed an ISO 27000 compliant infrastructure, which had an RTO and RPO of 4 hours and 15 minutes respectively. So if for those who are unaware of the term or new to the term RTO and RPO, RTO stands for recovery time objective. In short, how fast you can recover in an event of a disaster or disaster-like scenario. RPO stands for recovery point of objective. That is how much you can recover when a disaster happens. So for this instance, RTO of 4 hours means in an event of a disaster being declared, you can recover from the disaster within 4 hours. And an RPO of 15 minutes means you can recover, let's say the disaster happens now, so you can recover the data up until 15 minutes from now. So that's the overall definition of RTO and RPO. So this project was about building an infrastructure with an RTO limit of 4 hours and RPO of 15 minutes. So basically the objective was to build a fault-tolerant infrastructure following the ISO guidelines. Now the next question, or usual question which comes in when a requirement as critical as this comes, why did we go with a DC or a DRC, or in other words, an on-premise data center? Why not a cloud infrastructure? So the reasons are, this project was based out of Indonesia, and Indonesia's financial services, like many other countries, requires its customers' PII data to be localized within the country. So the data cannot leave the country. And that is why the applications had to be hosted within the country. And on ISO 27000 needed that it met the RTO and RPO requirements for disaster recovery. And they also had an SLA defined of 99.95%. And at that time, there was no certified cloud provider available in Indonesia, which can meet the financial services regulator or OJK requirement. So the entire setup had to be done on a traditional data center and data recovery center, as we used to do in the good old days or pre-cloud days. And these data center had to be located at least 40 kilometers away from each other. So at least they should be located such that they are not within the same disaster prone zone. Otherwise, disaster recovery would not mean anything if they are just sitting side by side, which is the case with many cloud providers in some regions, that though they have multiple regions or availability zones, but the disaster recovery and the data centers and the disaster recovery conditions do not meet their physical co-locations. So in order to meet the regulators and the ISO's guidelines, we had to go with the traditional on-premise data centers. And that is why we had to devise a solution. And here is what it looked like. So we had a primary data center, and we had a secondary data center, or you can say the replica or the mirror data center, which is ideally the disaster recovery center. And there was data replication happening between both. So for the user, they would use the primary site as the live endpoint. And in an event of a disaster, they would switch over to the mirror site or the disaster recovery site. So keeping this topology in mind, the disaster recovery center architecture looked like this. So this is the network topology of both the data centers and how they connected with each other. So if you see the first layer, the iNet VLAN, the inter-DC VLAN, this was the VLAN created on the hardware devices. So as I mentioned in the title of the talk, it is actually on bare metal and hardware devices. So this was the first layer, which was the switches that were used in this architecture, and these VLANs were on the hardware VLANs or the virtual LANs created there. So the inter-DC VLAN was meant to connect both the data center, and both of these data center were linked with a direct physical line. So they had connectivity within less than 1 millisecond, which is very important and crucial for data replication to happen. If your TTL is more than 1 millisecond, no data replication can happen. No network-based file share or data share can happen. So that is why we have to make sure that the connectivity is such that the data transfer speed or the TTL is less than 1 millisecond. So we had a similar setup there. So there was a VLAN between the switches between both the data centers, and there was a VLAN for the intranet or within for the localized LAN of that data center. So that was the first layer, which was on the hardware switches. The second layer was on and this is from where the virtualization started over the bare metal, because of course it was not we could not have done the kind of RTO and RTO if we did not introduce automation, and how we use that automation using Terraform. I'll talk about it in the next slide. But this is the layer from where the virtualization devices came into picture. So the first virtualization device that you see here is the NSX Edge. So this is a virtual network appliance provided by VMware. It basically has all the networking features like DHCP, VLANs, firewalls, load balancers, whatever you see in today's modern day cloud. So as a matter of fact, each cloud also works in a similar way where they have created their own virtualized layer on the hardware layer. So that was the layer for networking, and NSX was the NSX Edge, to be precise, was the appliance or the application which is provided by VMware for virtualized networking. So we use that for our networking within each of these data centers. So we had an NSX Edge which was connected to the inter-DC VLAN, then another NSX Edge on the other data center connected to the inter-DC VLAN. So in that way, they can the systems which are connecting to both networks can still communicate with each other when the rules are set. The third layer was the VLANs, which was meant for the applications and services. So here we had three layers, where one layer was for web application, or to be more accurate, it was the public facing applications. This architecture was a microservices based. We had the Kubernetes cluster, and we had load balancers who would be serving the front end for the the endpoint for the internet facing users. So the NSX VLAN had three layers. One was for the web facing or the public facing services or endpoint, and then comes the app VLAN, where actually the microservices were sitting. So that was the private layer, although they had outgoing internet access, but incoming internet was only restricted from the web VLAN. Then we had the data VLAN, where all the stateful applications, databases, Kafka clusters, etc. were situated. And finally, the fourth layer was the type on hypervisor. Because we had bare metals again, we had to use a type on hypervisor. We could not use other things. And the reason we use VMware is because it's a licensed software, and it comes in with enterprise support. And because it was a very critical service of financial services, we were handling customer data. We had to ensure that it is not just a one-time setup. Plus, the ISO certification that I mentioned about, this was not a one-time thing. It had to be done every year. This recertification had to be done. So this is a long-term setup that we were doing. So we chose to go with VMware because it had the requirements that fit the bare metal virtualization as well as the support and the features. So the fourth layer you can see at the hypervisor, where actually you can see the virtual machines are sitting. So you have all your VMs over there, and on top of those VMs, you see the clusters and the databases. And then this layer of hypervisor, so the vCenter on both the data center were linked with each other, and the databases sitting on the clusters on VMs on this one would replicate the data in here. So there was live replication going on between both. And when a disaster happened, we would switch over the DNS to the other side. We would do some pre-checks, and then we'll switch over the DNS to the other side, and then the user can continue accessing the application from the second side. And when the disaster recovery commences, we will revert back the same. So this is something, this is the architecture overall process of how we had set up the data center, and how the whole, the workflow happened in an event of a disaster. Or to say that we had to mimic this, and we had to record this to get ISO certified. So how did Terraform or infrastructure as code play in, or if I may say, we couldn't have done it within a short span of just 4 months if we did not have infrastructure as code in mind, and if we did not use infrastructure as code as a methodology to operate and orchestrate this entire setup. So how did we do that, and how Terraform played a key role in it? That's what I'm going to be showing in a demo now. So first up, what did we use Terraform for? So Terraform was used as first of all, was used as an orchestrator for creating environments on demand. So we had a staging environment for testing the setup, and then we had production environments, and then eventually we were also planning to have development environments and so on. So since we had the testing environments and production environments, we had to make sure that the environments were similar, at least logically, if not physically in terms of resources, but at least logically the architecture looks same. So we had to create an environment on demand, and Terraform played a role of an orchestrator in this case. So one thing we were sure when we were building it, that if we have to when we have to go with infrastructure as code, we were going with Terraform, and because of certain reasons. Because Terraform maintains, first, one of the features of Terraform is that it maintains state files, which is very important when you are setting up a long-term infrastructure, because the state of the infrastructure, to keep the record of the last state of the infrastructure, is very important, so that you can do changes, upgrades later, because we are not going to destroy the infrastructure every time we do a deployment, because this is going to be very critical, and it is on bare metal. So that is why the state the mechanism of storing state files on a backend was very important, and Terraform provided that. And those state files, when copied to an object storage on a cloud, can be version controlled as well, which was very good, because Terraform does not overwrite the state file, but it will just append the state files, and we can see what was different, what was before, what was later. So as an orchestrator, Terraform was provided there was a provider for vSphere for creating the virtual machines. However, Terraform did not provide any provider for NSX Edge, which was our networking appliance. In that scenario, since we were limited, had limited time, and did not have enough time to create a new provider for NSX, so we had to fall back on and the second configuration management tool, which was Ansible, because Ansible provided a ready-made module for NSX. However, it was only for configuring the NSX that we were using Ansible module. The execution still happened with Terraform. So I'm also going to show you how Terraform was used to provision the entire infrastructure using its own provider plus a third-party provider like Ansible. Plus, the fourth thing that we also had was a third-party object storage, because as I mentioned, we had to store these state files to know what, if we even have to do a RAM upgrade maybe 3 months later after the launch happened, we had to know that what was earlier, and we had to append it, because we cannot destroy the entire system. So we had to store the state files of the entire system. So for that, we used a third-party object storage, which was an S3, bucket. Uh, Although the infrastructure and PII data was all had to be stayed in Indonesia, but the state files were certified and sanitized such that it does not have any sensitive data, so it could be stored in a cloud provider's bucket. So there was a cloud provider which had limited resources at that time in Indonesia, so we could store it in that cloud provider. We did not go with that cloud because it was not certified, and we only had to use it for our backups and other storage. So that's how Terraform was introduced as an orchestrator. The second role that Terraform played here was a provisioner role. So basically, it was the deployer. So the last command that would be run was Terraform apply, and that would call all the other modules, be it Terraform modules for vSphere or be it Ansible modules for NSX. And in this case, while using Terraform as a provisioner, we structured it into a modular infrastructure as code rather than just a bunch of folders and writing infrastructure as code. So it was divided into different categories of modules. So there were base modules, there were provisioner modules, and then there were states, backends, and workspaces with respect to the environment. That is how the Terraform, as a provisioner, we created modular infrastructure as code. So let us look at how that modular infrastructure as code look like in Terraform. So this is what it looked like. So we had all the modules which were parameterized and created within our module. So you can see here the Ansible NSX. It's a module of you can say a playbook using the Ansible module of NSX. Then you have things like for network, for OpenVPN, and for virtual machines. So we have generic modules created for virtual machines, generic modules created for SSH, generic modules created for network. And then when we had to create provisioner, the provisioner would be to create the actual environment. So you can see that there is an administrative or management provisioner, there's a load balancer provisioner, there is a production provisioner, there is a staging provisioner. So each of these are Terraform modules, internally, but they play a different role. The idea is to increase reusability and portability. So because we wanted to have an environment on demand structure, we needed to make the modules as generic as possible so we can create the same kind of environments as many times as possible. So that is why we followed this structure. And as an example, suppose we had to create a VPN server, the vSphere provider, using the vSphere provider, we would just call the TFO VPN and it will be created. Likewise, if we have to create a single load balancer, we would call the TF load balancer, and then which is within the Ansible one, and then it would be created. So that's how the whole structure of our modules and provisional look like. Now, to give a quick overview of how it actually played with Ansible and Terraform that I mentioned earlier. So as I mentioned, Ansible had a pre-built module for NSX. So we decided we would use that because it would save some time. So we use the Ansible module, which gives you the configuration parameter as NSX Edge Firewall. So if it had various roles that we created. So using that module, NSX gives you feature to create firewall rules. Like in case of cloud, you have security group rules. In NSX, you can create firewall rules. What is the ingress and what is the egress. So likewise, we created roles for firewall. Say, what will be the ingress role for DB? What will be the ingress role for external, the public traffic? What will be the ingress role for HTTP, for SSH, for UDP? And what will be the overall firewall rule? Similarly, we created DHCP rules where we create a DHCP pool for the internal network, which is similar to how you create the VPC pool in case of a cloud. Likewise, we had other configurations. Let's say load balancer was a very important one, where it would actually use the load balancer function of NSX, and it would create a load balancer endpoint. And it was very important and very widely used, because we had a public facing application and we had microservices, so we had to create multiple load balancer endpoints for different services that were created in Kubernetes. Likewise, and then we had the NAT rules. So NAT is again for allowing outgoing traffic, internet traffic, etc. SNAT and DNAT rules. So these were all the rules that were created using the NSX Ansible for NSX. This product is now deprecated. They have a new product of NSXT, but it was 2-3 years back. So we used that product at that time. So Ansible, if you go to Git, you will find the Ansible and NSX repository, NSXT, so you can have a look at it. So these were the roles that were created in Ansible for creating firewall, DHCP pool, load balancer endpoints, and NAT. Now, when we had to use that in our network, let's say we want to create an app tier or a data tier, like I showed in the VLAN diagram earlier. So let's say we have to create the app tier. We would first call the Ansible repository, which was, we will clone the Ansible module repository, and then there were templates created for firewall rules, and then in app tier you would use that template, and you would have variables which will map to these respective IP addresses, internet name, or edge name. So for example, for web we had DHCP pool and gateway IPs and all of these. So you had all these maps created for each of these network, and then when you had to actually deploy them, let's say we are creating the administrative, or let's say we are creating the staging network, and what we would do is we would just call the network module here, and that will go and call the Ansible code in here. Let's say app tier, it will call this code. So how it will deploy is this way. So this way it will create the environment, and NSX manager. It will call the map, which is basically the IP addresses and all the parameters that we had defined earlier, which was parameterized. So we would use Terraform template to deploy it, and then we would configure all these layers. So likewise, in network, you have firewall rules, and then also the NAT rules all were created. So although we used an Ansible module, but we were using Terraform to call it. And that way we could actually combine both Terraform and Ansible modules together. So for network, it is, you can see like this. Similarly, you can see the network configuration is like that. And if you have to configure a Kafka cluster, then we were calling the vSphere modules to create the Kafka cluster. And likewise, if we have to create a GitLab runner, or let's say VPN server, so we would actually go ahead and create a VPN server and load balancer, which will call it the load balancer module, and a similar way. So this way, Terraform was used as a provisioner, and that way, what we achieved is that we had modules and we had environment specific provisioner, and Terraform was the orchestrator. And when we had to do the DC DRC drill to record the ISO compliance, we could just use these applications to create the entire infrastructure, and to do the switchover of the data transfer, and to showcase that in an event of a disaster, we can get an entire infrastructure up and running within a time limit of 4 hours. So infrastructure as code played a huge role in this case, because it was on bare metals and on type 1 hypervisors and virtual appliances, and everything was hardware and physical, right? We didn't have the leverage of cloud, the flexibility of cloud services. So using Terraform and infrastructure as a code as a practice, we were able to achieve this whole setup, which was the DC-DRC with an RTO of 4 hours and RPO of 15 minutes, which was compliant with ISO 27000. So what we achieved in the end, the final thing is, in short, it was not, it would not be wrong to say that we actually got an on-premise automated environment on demand, or if I would actually like to call it a private cloud or an on-premise cloud using infrastructure as code. So the infrastructure was built in a fault-aware architecture. It had secure and seamless connectivity. The system was protected not just physically but logically as well, because we have different network, different VLANs for different layers of the application plus different environments. It was automated, modular, and reusable across different environments. If we had to create 5 different environments in down the line, we would be able to create it with the same architecture of ISO compliance. It also had a centralized role because Terraform within Git, it was used as an orchestrator. So we had a centralized mechanism from where we could control all the parameters, all the values and configurations of the infrastructure. And this also helped enable the scheduled assessment of the disaster recovery. As I mentioned, every year we had to do this ISO compliance. So it was not possible if we had to rebuild the entire infrastructure next year and the year after. So this infrastructure as code actually helped us to take that load of our head, because it is a one-time setup and we do not have to do any changes. We only have to probably create a new environment and do a drill, and then we would be done. A very important, we also used a framework called the 10-factor infrastructure, which played a key role in designing this entire architecture that I showed earlier, which is actually a framework to build a security, scalability, and sustainability as a first-class principle of infrastructure code. So it provides 10 factors which are needed for your infrastructure for these features. So it had network with seamless and secure connectivity, system with stable and scalable setup. As I mentioned, it had Kubernetes cluster, so we could scale it out. Again, I did not have much time to explain how we did in Kubernetes because we were using virtualization Kubernetes way, using Kubespray. So that was also used, again, a self-managed Kubernetes cluster. Then we had storage, which was a separate hardware device again, which was launched into the VM. Then we had identity management, and I had showed in the demo that we had a VPN module, which was essentially using OpenVPN software, which would give role-based access control on specific environments. So not everybody will have access to production, only specific people, and that we controlled using the VPN. And then we had securities, like we saw the firewall rules, the NAT rules, the different subnetting, and the VPN rules, the load balancers were all on SSL. So that was part of security. Then we had logging and monitoring. We had the standalone, a self-managed logging systems and monitoring system for this entire thing. And as we described in this session, it was an HA setup, although it was not an active HA, it was an active passive HA, but there was still HA available in an event of a disaster. We could still fall back and we could meet the RTO and RPO and SLA that we had defined. Of course, it had the disaster recovery center and environment on demand, which was provided by using Terraform as an orchestrator and infrastructure as code. So this is the 10-factor infrastructure framework that we utilized in designing the architecture that you have seen. If you want to know more about this project, we do not have much time, I guess. If you want to know more, so you can connect with me. I would be happy to share more in details on how each of these components was devised. This is my website link, and this is my podcast link, where I have actually published 10 episodes on this 10-factor infrastructure, and I go much in-depth analysis of how this was done, and there are much more details in there. And of course, you can follow me on social media, on LinkedIn, and I guess we can proceed with the next session and with the questionnaire. So thank you so much for providing the opportunity and for being in this talk.